Okay, so what I just gave you was a list of topics through basically through where we were on Wednesday through chapter 3. So as I'm going through as I go through the textbook, these are the kinds of things that I think you should be able to know how to do for the exam next week.
Is it just 1 through 3?
I'll clarify that the end of class.
So is it multiple choice or is it short answer? Or did you decide?
It could be a combination of both.
For the naming?
For the naming, combination of both as well. So next week, after I think about it a little bit more, I'll narrow down some of that. But I would imagine you're going to have to write out the entire name, but then for some of the more complicated ones, you might have to get a multiple choice. So if you go through this list, and you can do all these things, then you should be in pretty good shape. So that's just the list there. So we left off on Wednesday looking at a two-step mechanism, this example two-step mechanism, where we had one intermediate, which was our carbocation intermediate, and then we talked about Hammonds Postulate, which basically says that if you're in a one-step process where there's just a transition state, that in general, if you lower the energy of the product, you will lower the activation energy and therefore make the reaction go faster. And so that's how we explained that a tertiary carbocation is going to react faster than a secondary carbocation in that two-step mechanism, because the formation of the carbocation is the rate-determining step. Okay. So then we were going to go to a little bit more complicated situation. And this would be the more complicated situation. So I'm going to start with a carbocation as an intermediate. And I'm going to give that carbocation two pathways to go in. The pathway to the left and the pathway to the right. And so I think we ended class on Wednesday by saying, which way is it going to go the fastest? Is it going to go to the left or is it going to go to the right? Left? Are we sure about that? No? Does that mean you want to go to the right?
No.
It depends. Okay. What's it depend on? Well, let's deal with that.
Is it the heat in the environment?
Could be. Let's deal with that. So, which reaction is going to go faster? Is it going to go left or right? Which one is going to go faster? And there's no depends. The depends going to be what the major product is, whether it's going to be the product on the right or the left. But we'll get to that. Give me 29 minutes and we'll get there. So the reaction that's going to occur fastest is the one to the left. Why? Lower activation energy. So there's my activation energy for the reaction to the left. Here's my activation energy to the right. I guess I should ask this question then. Is there ever a time when the reaction to the left is not going to be faster than the reaction to the right? What? Yeah, and I'm not going to change the reaction coordinate diagram. The catalyst would then lower the activation energy, maybe on both sides, but I'm not going to going to do that with a catalyst. So just the way it's written, is there ever a time when the reaction on the left will not be faster than the one on the right?
Maybe if it's endothermic?
Again, I'm not going to change the reaction coordinate diagram. So
I don't know, if it wasn't more stable at the end.
yeah, but that's still a higher activation energy, right? So there isn't. I kind of got a sense that maybe some people wanted to say, oh, well, I can make it go over the right-hand barrier faster than the left-hand barrier. The math doesn't work out that way. So remember that the rate of the reaction is equal to the Arrhenius equation of A to the minus EA over RT. And the most important part of that is activation energy and temperature. It's a logarithmic function. The lower the activation energy, the faster the reaction. The higher the temperature, the faster the reaction, and vice versa. So there is no way to make the reaction go faster over the left barrier if it's smaller. All right, so that's one ground rule I'm going to lay down. We can't make it go over the right barrier faster than the left. We could get them to nearly identical rates if we raise the temperature high enough. We can get them to almost go over the barriers at the same rate, but it'll still go over the left barrier faster than the right barrier. Everybody okay with that? So, this reaction is faster. The one to the left because it's got a lower activation energy. Now, let's imagine we do this reaction for a short period of time. Most of our product is on the left because it's gone over that barrier faster. If I want the left product to be the major product of this reaction, then what I should do is I should stop the reaction after a short period of time. Because after a short period of time, you're going to have more left-hand product than right-hand product. Because it'll go over that barrier faster. Okay, everybody agree with that? So, short, that left is going to be the major product when I use short reaction times. Is there another way that I can make the left product, ensure that the left product is the major product? Run it at a lower temperature. Now, how does that increase the amount of left product relative to right?
Because you need more heat or energy to make it go to the right. So it's at a lower temperature, you're only going to have that let it go.
Okay, so if I minimize the energy, there would be a break point where it really couldn't go over the right hand, but then I'd have to be careful that it can make it over the left. So if I limit the amount of energy in the molecule or in the reaction, I can get it to go over the left barrier faster, or go over the left barrier more often than the right barrier. Right. So the example here would be like hikers or birds going over the mountain. Like the birds better. So when the birds have a lot of energy, they can go over both mountains, but they'll go over the left lower mountain faster. If we made hypersonic birds, then they would go over both barriers and both mountains, but they still would go over the left one a little bit more. And of course, if we have birds near death because they have no energy, they're going to crash into the side of the big mountain and just barely make it over the small mountain. Okay. We could do the same thing with hikers too, except I don't know how to get hypersonic hikers. So if we limit the energy, we're going to get more left product than right product. We'll still get a little bit of right product because remember that what we're really talking about here is kinetic energy. The kinetic energy of molecules, the average kinetic energy, is proportional to temperature. So when I lower the temperature, I lower the kinetic energy. And these molecules are crashing into each other, and there's a whole distribution. In the book, they have the Boltzmann distribution, so there's a whole distribution of kinetic energies, but more often than not, they're going to go over the left barrier than the right barrier. So if I want to favor the left product, use short reaction times and lower temperatures. Whatever that means, and that's going to depend on the reaction. So then the question becomes, how do I form the right product? The product on the right pathway. And the first thing you say is, but most of it's in the left, as left product. Right? Well, what happens is these reactions are reversible. So that even though I'm at the left product, I can go back to the carbocation intermediate. Now, you might have a hard time picturing that. Let's look at an example. So let's say that I have my alkyl halide and I'm going to break my carbon-chlorine bond. I'm going to make my carbocation, and I'm just going to say I lose the chloride here. Okay. So what kind of halide did I start with? Primary, secondary, tertiary? Tertiary. That I didn't put on the list, but if you don't know, you want to put that one on the list, make sure you can tell the difference between primary, secondary, and tertiary. So I form this carbocation. Now, if I form this carbocation, let's just say for the sake of argument that I want to react it with a neutral nucleophile. In other words, something that's electron rich but doesn't have a negative charge. Well, the perfect example of that is water. So if I want to react this carbocation with water, the water is going to donate its pair of electrons to the carbocation, and the product that I'm going to make has the oxygen attached to the carbon. The oxygen has two hydrogens attached to it. We're going to find that neutral nucleophiles don't break apart. The whole thing reacts. And we end up with the oxygen with the lone pair. Its formal charge is +1. Which makes sense because I reacted a +1 with a neutral species. There better be a +1 on the other side. And so the oxygen has a positive charge. This species we would call a carbocation, and this species over here we would call an oxonium ion, is what it's called. You could also call the carbon a carbonium ion, but I like carbocation better. Right, so the entire water molecule adds, and I end up with my oxonium ion. The oxygen's not happy with the +1 charge, so one of the OH bonds breaks and gives a pair of electrons to the oxygen. Restoring the oxygen to having two lone pairs, but releasing an H+. So basically the OH bond breaks, the oxygen gets a pair of electrons, and the hydrogen gets nothing. It becomes a positive charge. This is a 3-step mechanism, because what we find is that when we react tertiary halides with a neutral nucleophile, we don't have a 2-step mechanism. Instead, we have a 3-step mechanism. Now, what was my point of going through this? What was my point? Oh, reversibility. See, I just do that for effect. I didn't really... Well, if I say that now, I do that for effect, and I really didn't lose my place, then you'll believe me the next time, and when I really lose my place. So it's the reversibility. So let's say you have an OH as the nucleophile. You've got an H plus as an electrophile. So the oxygen donates its pair of electrons to the H plus, and what happens? We reverse the reaction. And then if I have an oxygen with a positive charge, basically a water molecule here, I could break the carbon-oxygen bond and give that pair of electrons back to the oxygen, and I could reverse the reaction here to form a carbocation. So this is an example of a reaction that's reversible. So if I form an alcohol in the presence of acid, the acid can react with the alcohol, and I can go right back to the carbocation. So that's an example where it is reversible. And so if I go back to my diagram, if I'm sitting over here at the left product, let's say I could reverse that to go back to the carbocation. How much energy is that going to cost? Or how much energy is that going to cost me? Well, now I have a second activation energy for the reverse reaction. Now, the left product is not as stable as the right. So the left product is not as low in energy as the right. Okay. Now, how am I going to get that left product to reverse? I'm going to have to give the system...
More left product. Add more of the left product.
Well, I'm not adding anything. So what I've got is I've got left product, but I want it to reverse itself back to the carbocation. What does the system need to have a lot of? Heat, energy, so that I can overcome this large activation barrier. So now I'm going to talk about, well, how am I going to favor the right-hand product? And one of the things I'm going to have to do is I'm going to have higher temperatures. But here's the thing about higher temperatures. While higher temperatures may produce a little bit more of the right-handed product, you're still going to get more left-handed initially.
Wait, why is there a second activation here?
Because anytime you have a reaction that goes like this, going this way, well, let's see. Yeah. In this case, we're going, the small activation energy is when we're going from this as my intermediate to the final product. But if I want to go in this direction, I've got to go from here to here, so then the activation energy gets bigger. So when the reaction has higher temperatures, then I'm still going to produce more L than R. But given enough time, some of the L product is going to end up back in the carbocation. And then it may still go over the barrier to give me more L, but occasionally, once in a while, particularly if it has enough energy, it's going to go over the larger barrier and end up down here in the right-handed product. And now, because the right-handed product is more stable, it has a much, much bigger activation energy. So now if I end up with an R product, it's going to take a lot more energy to get that back over that much, much bigger barrier to get me back to the intermediate. So this barrier of the reverse reaction is much bigger than this barrier. And so what does that mean? If you give this reaction enough time and enough energy, most of the product's going to end up as right, as the R product, because it's going to be stuck there and not able to undergo that big barrier to get me backwards. So if I want to favor the R product, I'm going to use a long reaction time and higher temperatures. Does that kind of make sense? So initially I form L, but then over the time period, with enough energy, everything ends up like in R, in this sort of in the sink. If you want to think of this as like a thermodynamic sink, everything ends up there because it can't get out. It ends up in that well. So this is a little bit more of a complicated reaction, but this gets to the idea of what the book called kinetic control and what's called thermodynamic control or conditions. So there are some reactions where you can pick and choose your product depending on what the reaction conditions are. So if you've got short times, low temperatures, you're going to get the kinetic product. If you have long time reactions of long time and higher temperatures, you're going to get the thermodynamic, what we call product. Now the thermodynamic product is always the most stable product. And as I'll show you in a moment, the kinetic product actually comes from the more stable intermediate. And I know there's only one intermediate there, so how am I going to make that up? I'll show you. So the thermodynamic product is always the most stable one. So when you want to favor it, long time, lots of energy. You want to favor the kinetic product, short times and short reactions. Short times and short and low temperatures. Or lower temperatures.
Now, if you were to put this to use in a lab, would you raise the temperatures, let a certain amount go over, then lower the temperatures, separate out that substance, that product on the right side, and then do it again until you get all the product out?
I mean, you could. You're going to end up with an equilibrium between the left. You're still going to end up with some left product. The thing here is you could go from like 30-70 to 70-30 by changing the conditions. And I suppose if you played with the temperature enough, you might be able to go 90-10 and then 10-90, depending on how you wanted to do that. But the most important thing here is, in this process, we can read this energy coordinate diagram and draw those conclusions. So the lower the activation energy, the faster the reaction goes, and then what's the effect of the product stability on getting back out? Because I think what I said at the end of class was something like a reaction diagram. A reaction's not a highway. It's not a two-dimensional thing. It's more like being in a valley surrounded by mountains. And you don't know how deep the other valley is behind that mountain. You have no idea. So the reactions will go over the barriers the first time. They're dictated totally by the size of the mountain. Coming back to that original valley is going to be dictated by how stable the product is. And you don't know. The rules are, depending on how much energy you have, you're going to go over the smaller barrier first. Does that kind of make sense? Now, what I did this morning was I took my life in my hands and said, let me show you a reaction, a real reaction that this corresponds to. And we need to know, I think, 2 additional things, but everything else we know. So let's say that I reacted an H plus with this diene, which we would call 1,3-butane or butan or butadiene. So that's 1,3 I think it's butane diene instead of butadiene. But butadiene is like its common name. So this is the chemical that when it reacts with itself forms long chains and basically makes rubber. So this is what you make tires out of. And this is what the rubber tree plant makes rubber out of, is butadiene. So H plus is what kind of molecule? Electrophile, nucleophile? H plus. Electrophile. The double bond is a nucleophile. So what the double bond can do is donate a pair of electrons to the hydrogen. Now, unfortunately, when it does that, only one of those two carbons can form the bond. And so I'm going to say that the hydrogen-carbon bond that's formed is going to be to the end. And that means that the second carbon, carbon number 2 in this, it just lost an electron because carbon number 1 gave that electron to form the carbon-hydrogen bond. So carbon 2 is now a plus charge. And it didn't have a choice. Okay, so there's my first intermediate. There's a resonance structure for this. How do I draw it?
Is it mirroring it essentially so that the methyl group is on the right side?
Nope.
No.
Can't move. We can't rotate the molecule around. If you wanted to do that. Not allowed. All I can do is move a pair of electrons.
Is it like the E group is on the carbon on this way?
So take the electrons from this and do what?
Put on the other one.
Do that with the arrow. Yes? This is number 6 on that sheet. Being able to draw resonance structures by moving electrons with arrows. Right, there were a couple of those in the book. There was 2 of them I put on the worksheet. So the pair of electrons always moves towards the positive charge. Negative always moves towards positive. So that's going to leave me with a resonance structure that looks like this. And now where does the plus charge go? Where? To the end. So now the plus charge is going to be on the end. And I could have an arrow on the molecule on the right, the resonance structure on the right to get me back to the middle. Question. Which of those 2 carbocations most stable? What?
I thought you could only move like the plus charge 1 carbon at a time.
No, the plus charge actually moves. It has to move 2 carbons. The pair of electrons moves 1, and then the carbon's got to move 2 carbons away. So you can only move a pair of electrons 1 bond, but the resulting plus charge can only move 2, or will move 2 if you want to think of it that way. Because what happened was this bond, we took this pair of electrons to give it here. This carbon's fine because it didn't lose anything, but this carbon got the shaft because it lost the 1 electron because this carbon gave it to that one. So it's back to plus charge. So they'll move, plus charge will move 2 carbons. The bond will move 1.
So can I answer the stable?
Sure, take a shot.
So would it be the first resonance structure because the carbocation is secondary? It's attached to it.
Okay? So I hear that this is secondary. This is a secondary carbocation. Does that sound like a good answer? Well, only compared to what's the other carbocation? A primary carbocation. But wait, I'm never allowed to write primary carbocations, right? I mean, that's the third rule. Right? Don't take the class, no five bonds of carbons, no primary carbocation. I don't think it goes much past 3 either. If it did, there'd be t-shirts. Right? Top 10 things. Bobby?
So why is that first one a secondary carbon cation and only one carbon attached to it?
This one?
Yeah.
So there's a hydrogen there, and there's 2 carbon groups attached to it. So it has a total of 3 bonds. That's what gives it the plus charge.
There's only one carbon directly attached to it.
No, there's another carbon here. I just didn't show it.
Well, yeah, but in that case, there's 2 carbons on the other one too, and you only said that's a primary carbon.
No, let's see. This is a CH2 with a carbon with an H there. So that has 1 carbon attached to it.
There's a C right on the other side of the double bond too.
Not directly attached to the C+.
Oh.
It's only, yes.
Okay.
So whenever I say a tertiary carbon, I have to really define what carbon that is. In this case, what I'm saying is the carbon with the plus charge is attached to 2 other carbons. That makes it secondary. Over here, this carbon is only attached to 1 carbon, so it's primary. Okay. Except the primary carbocation I'm allowed to draw. And it actually would exist because of this. This primary carbocation has another resonance structure. The more resonance structures you have, the more stable you are. So this primary carbocation would actually be called, later on we'll call this an allylic carbocation because it's on a carbon next to a double bond, and that's called the allylic carbon. But that carbocation has an additional resonance structure. Your run-of-the-mill primary carbocations don't normally have resonance structures. And so that's normally why we don't draw them. But this does have an additional resonance structure over here, and so it turns out that it's a little more stable than a primary carbocation, which makes it valid. So I've got a secondary and a primary. Which one's more stable? This one is. Now, let's finish this reaction off. I need a nucleophile to come in and react with each one of those 2 carbons. So let's make a simple nucleophile. Let's say I've got a Cl- that comes in, adds to that carbocation. I've got a Cl- that comes in and adds to the primary carbocation. So what's my final product going to be? There are my 2 final products. So in essence, this is a 2-step mechanism where the intermediate has 2 resonance structures.
Would the arrows be filled in for the transfer of electrons from chlorine to the carbocation?
Yes, they would be full-blown. These are full-blown arrows. To be honest, I don't think we're going to use half arrows through the remainder of the semester, although I might take that back. In this book, free radical reactions are in second semester, not first semester.
When you're drawing them on the board, will you only do like half an arrowhead
Yeah.
to indicate?
I'll try. So these are full arrows. So now I got two products. I got product A and B. You know what my next question wants to be, right? What's my next question? I heard it.
Which one's more stable?
Which one's more stable? Well, I'd ask you that question, except I don't know that we know the rule for that yet. Because which double bond is more stable? And that's a rhetorical question that I'll answer. So it turns out that double bonds become more stable when electron density gets pushed into them. Okay. So the more electron density that gets pushed into a double bond, the more stable it is. Well, how do I push electron density into a double bond? The same way I pushed electron density into a carbocation. So if I attach an alkyl group to this double bond, the carbon's slightly negative and each of the hydrogens is slightly positive. And so now what can that carbon do? It can push a little bit of electron density in a double bond and make it more stable. So 4 alkyl groups, most stable, then 3, then 2, then 1. So this is exactly what we learned with carbocations. So I think I said we'd use this principle of the carbon being slightly negative and the hydrogen being slightly positive in like 5 or 6 other explanations. This is explanation number 2. Why is a tertiary carbocation more stable than a secondary one? Because it's got 3 methyl groups pushing electron density. Why is the more substituted double bond more stable? Because it's got more alkyl groups pushing. So given that explanation, which product is more stable, A or B? I heard a B. Do we like that? Yes, no. Yeah, I got it to B. But there's not very many people agreeing or disagreeing with that.
We're asking about the product, right, not the intermediate?
Yes. The intermediate is more dependent on the carbocation type than the double bond. The product is solely based on the double bond.
Wait, so the top ones that we were talking about, that's the intermediate,
These are the intermediates.
and then the bottom.
These are the products. So this is after the chlorine comes in, attacks, or reacts with the carbocation to make these. So these are the 2 products. So if we're all, so maybe that was a point of confusion. I don't think so, but. So we still think B is the more stable product? How many alkyl groups attached to B? How many alkyl groups attached to double bond? How many attached to product A?
1.
Anybody not see that? I'll just assume. So here's what we know about double bonds. We know double bonds have 4 attachments, right? Where did we learn that? Cis, trans, EZ. So when I look at A, if I don't quite see that, what I'm likely to do is I'm likely to put in my hydrogens. So that when I look at A, how many hydrogens are attached to that double bond? 3. Well, it's got a maximum of 4 things. What's the fourth thing? A carbon group. For product B, I've got 2 hydrogens. That means I've got 2 alkyl groups. So you can determine that by either the numbers of hydrogens or explicitly say, oh, this one has 1 carbon group. This one over here has 2 carbon groups.
Is there any element that has a lower electronegativity than carbon other than hydrogen?
That would make it more negative? That would make it delta minus?
Yeah.
Yeah, there's going to be boron and aluminum and some of those metalloids. But we'll get to those later. So, which one was more stable? B. Okay, what was the point of this? The point is to give you an idea of a reaction that has a kinetic and a thermodynamic element here. In order for the kinetic and the thermodynamic elements to be there, basically the most stable intermediate has to produce the less stable product. And the less stable intermediate produces the more stable product. Because if the more stable intermediate produces the more stable product, game's over. There's no conundrum. But if the more stable intermediate produces the less stable product, and the opposite's true, now I have the ability to change the reaction product by changing the temperatures. So let's take a look at this one. So in this case, the primary carbocation gave the more stable product, but the secondary carbocation gave the less stable product. So it would have exactly the same diagram as what we were looking at. Sort of. What I'm doing is I'm oversimplifying things. Because what's the true intermediate here between these two resonance structures? It's the hybrid. So when I had just one intermediate, I was going from the hybrid. And then I have to translate, well, okay, what about activation energy? Well, if you're reacting with the less stable intermediate, the less stable resonance structure, you have a higher activation energy. And if you react with the more stable intermediate, you have a lower activation energy. Okay. But we'll come back to this. So the idea is here, there are reactions that you can change the products by changing the reaction conditions, but they will all have that same principle, that your more stable intermediate always gives the less stable product and vice versa. Because those factors are fighting against each other. So this is actually what kinetic and thermodynamic, our first application of this, and probably our only application of it. So when we do this next semester, I'll say, oh, remember in the first semester when we did this, and nobody will. So then we'll go back over it really quickly. Okay. But we can understand this diagram from activation energy and final product stability. And that's really what Chapter 3 is trying to get us to do. All right, everybody okay with that? So the only thing left in Chapter 3 was carbocation rearrangements. And basically what happens is that if you have, for carbocation rearrangements, if you had a secondary carbocation and you had the possibility of having that hydrogen on a carbon next to it slide itself over as an H minus, then you will get the plus charge moving in the opposite direction. So that H minus is moving as, that hydrogen is moving as an H minus. So it's like the hydrogen grabs both of its electrons and slides over to the carbon next to it, to the carbocation. And what would be the driving force for this to happen? Why would that hydrogen want to pick up and move to the carbon next to it?
Is it the alkyl groups on the sides repelling it away to the other one?
There's no repelling going on.
So it's more stable.
Which one?
The one, right.
So this is what kind of carbocation? This is a tertiary carbocation. What kind of carbocation is this? Secondary. So the rule for carbocation rearrangements is that it always goes to form the more stable carbocation. So you go from secondary to tertiary. Sometimes you could go from potentially primary to tertiary. But if you go secondary to secondary, I didn't gain anything. The idea here is that the stability that you gain, that energy, is what you use to get the hydrogen to move. Because there's a barrier, there's a activated complex, there's a transition state for that. And so it costs energy. But you get that energy out, you form a more stable carbocation. That's the basics for those. So just in terms of the book problems, it's not something I would necessarily ask on an exam, but it is something that might be in the book problems. So chapter 4 is what we'll talk about on Monday, which is we're not even the good organic stuff yet. Cyclohexanes and Newman projections. I mean, we're not even there yet, but we will be by the end of the coming week after the exam. So as far as the I got a minute I'm going to use. When we're talking about acid-base reactions, what we want to do is just make sure that there's one principle that's going to guide us throughout this entire, in terms of acid-base chemistry. The base, or the acid in this case, makes a conjugate base. The conjugate base is the opposite of the acid. And I would like, if I want to make a weaker or a stronger acid, there's just one principle that I have to work with. And that is somehow I've got to push the equilibrium to the right to make it stronger, or not push it to the right to make it weaker. And the way I do that is not through Le Chatelier's principle, because there's only one thing here. Le Chatelier required two things to have one in excess. When you just have one thing, you can add more, but you don't change the equilibrium. Instead, what I'm going to do is I want to make this product, the conjugate base, more stable. So anything I can do to make that more stable is going to push the equilibrium to the right. So for instance, a carboxylic acid is much stronger an acid than an alcohol. Actually, the alcohol is not even really an acid. It does not dissociate much. But a carboxylic acid does, which makes this more stable than this. Why is this one more stable? Because it has one more what can I do with that lone pair of the negative charge? And what did I just make? Its resonance structure. So the deprotonated carboxylic acid has another resonance structure, makes it more stable, makes the carboxylic acid a stronger acid. So on Monday, we'll go back and talk about the first part of chapter 4. The reading assignment will be into the middle, or be in the next couple sections. But this is the principle we have to use over and over again. Okay? All right, if you have questions, feel free to email me or stop by. Then on Monday, we'll go through the acids and we'll figure out what should be on Friday's exam.